We've spent time defining reference frames. In this case, we see an inertial reference frame that has three basis vectors, e sub 1, e sub 2, and e sub 3. And we've begun to define vectors using the basis vectors within the reference frame. So for example, we see the position vector of p with respect to O, and this is defined as the length r1 in the e1 direction plus r2 in the e2 direction plus r3 in the e3 direction. Now it's time to take the time derivative of the position vector to get a velocity vector, and then the time derivative of a velocity vector to get an acceleration vector. And what we'll see is that the choice of reference frame in which we observe that time derivative makes a big difference in what that vector actually is. So let's start by writing out the velocity of p with respect to O as observed in the inertial reference frame. So this will be the time derivative in the inertial reference frame of our position vector r of p with respect to O. And so we'll start and work term by term. And so when we take the time derivative as observed in the inertial reference frame of r1 e1, we have to use the product rule, and we get the time derivative in the inertial reference frame of the scalar r1, which is a function of t, multiplied times the basis vector e1, plus r1 is a function of t multiplied times the time derivative of the basis vector e1 as observed in the inertial reference frame. We continue on to the second term, and then the third term, and you see that in both cases we're repeating the pattern using the product rule. And as we take a look at these first terms on each line, we see that the time derivative of the scalar r1, r2, and r3 actually means something, because the position vector in each of these three directions, e1 and e2 and e3, is going to change length. However, when we look at the second term, we have that r1, which is our scalar, is multiplied times the time derivative of the basis vector e1. And we see that pattern e2 and e3. And the time derivative of a basis vector that's fixed in the inertial reference frame, when observed in that inertial reference frame, is going to be 0. And that's going to be 0 for all circumstances. And so then we see that the velocity of p with respect to O as observed in the inertial reference frame is equal to r dot 1 in the e1 direction plus r dot 2 in the e2 direction plus r dot 3 in the e3 direction. Now this really shouldn't come as any big surprise, because we defined our position vector within the inertial reference frame, and in this case we took our time derivative as observed in the inertial reference frame. And so this means that when we take our second time derivative, which is the acceleration of p with respect to O as observed in the inertial reference frame, we'll get r1 double dot in the e1 direction plus r2 double dot in the e2 direction plus r3 double dot in the e3 direction. So now let's consider a situation in which we have observed the time derivative of this same position vector, r of p with respect to O, but we do it from a different reference frame. So let's create a reference frame A. And so here reference frame A is defined by the origin O prime, and then the basis vectors A1, A2, and A3, which create an orthogonal basis. Then we'll also say that the reference frame A is moving relative to the reference frame I. And so it's moving in an arbitrary path, but then is also rotating as it moves along. And so let's take the time derivative of the position vector as observed in the A frame. And so we'll find the velocity of p with respect to O, but as observed in the A frame. And so this means we're taking the time derivative as observed in the A frame of r p with respect to O. And so we use the product rule to get this expression, in which we have the time derivative of scalars 1, r2, and r3 multiplied times the basis vectors e1 and e2 and e3. And we know that the time derivative of a scalar doesn't matter what reference frame it's being observed from, and so this would be r1 dot, this is r2 dot, and then r3 dot, and then multiplied times E1, E2, and E3 respectively. However, take a look at our second expression, where we have the scalar r1 multiplied times the time derivative of the E1 vector as observed in the A frame. And so, if we consider what's going on, what we have is that our A reference frame is moving along a path, and we said it's also potentially rotating. And so that means that if you are located in the A frame, and remember our working definition, our conceptual definition of a reference frame is that it's the same as a rigid body. So let's say you're standing on this rigid body, and then you're observing the E1 vector. Then if you're tumbling and moving, then that means that the E1 vector, when you observe it, looks like it's moving. So our time derivative of the E1 vector, as observed in the reference frame that we're now observing it in, is not equal to 0. And that goes the same for the time derivative of the E2 vector as observed in the A frame, and the time derivative of the E3 vector as observed in the A frame. And then, when you differentiate this expression one more time to obtain the acceleration of p with respect to O as observed in the A frame, then it gets even more messy because now we're piling on the product rule of these time derivatives that don't go to 0. And so what we're seeing here by these mathematics is that when you take the time derivative of a vector, it absolutely matters which reference frame you make the observation. And so you're probably thinking right now, well, I'll just put all of my vectors into an inertial basis, and that makes my time derivatives much more easy because the time derivative of the basis vectors themselves go to 0, and I only have to deal with scalar values. And so what you'll find by doing that are a couple problems. The first one is that you lose intuition about what the system is actually doing, and then secondly is that the mathematics actually become pretty darn difficult. And so we'll be using other reference frames other than the inertial reference frame, and this will be starting next time, and we'll find out where those are useful and how we can apply our reference frames to specific problems so that we maximize our interpretation of the problem and also minimize the amount of algebra that we have to do to calculate those derivatives.